Welcome back, everyone. In this video, we're still continuing to find the derivatives of different types of functions. And in this video, we're going to focus on the derivative of the natural logarithm and exponential functions. And that's all exponential functions, not just e to the x. Now, I know that you saw logarithms in your pre-calculus course, but I want to review them just a little bit here in case it's been a while. And the notation for this is log base a of x, and if that's equal to c, that's the same thing as saying that a to the c is equal to x. If you see log base a of x, that's really asking a question. It's asking what power of a will give me x, and that would be the answer to log base a of x. Now when a is equal to e, we call this the natural logarithm. And e is a number that's very special in calculus and really in all of math, and so whenever it shows up, it tends to get a special name. And in this case, the logarithm with the base of e is the natural logarithm. And the way that you write it is ln of x. But when you see ln of x, just remember that's the same thing as logarithm base e of x, and you would treat it the exact same way. Now, natural logarithm has all of the same algebraic properties as the general logarithm that you would have seen in your pre-calculus course, but I'll review them here. The first is that if I have the natural log of a product, say a times b, I can break that up into the sum of natural log of a plus natural log of b. The next is very similar, but instead of a product we have a quotient, and instead of a sum it's a difference. And the third says that if I have the natural log of something raised to a power, I can take that power and bring it out in front of the natural logarithm. The next one is that the natural log of e to the x is equal to x, and this is because natural logarithm is a logarithm base e, and so natural log of e to the x is the power that you'd have to raise e to get e to the x, and that's just x. And very similarly, e to the natural log of x is equal to x. And this shows that e to the x and natural log of x are the inverse of each other. If you compose them together, you get right back to where you started. Now it's time to bring it back to calculus and ask, what is the derivative of the natural log function? And the way we're going to find that is by starting with an identity that we know to be true, and then taking the derivative of both sides, and then doing some clever manipulation to find the derivative of natural log of x. And to start, let's just write the equation e to the natural log of x is equal to x. And we know that's a true equation because that's one of the properties from the previous slide. And so let's take the derivative of both sides of this, and the equation is still true that the derivative of e to the natural log of x is equal to the derivative of x. And the derivative of the left-hand side is going to require the chain rule because e to the natural log of x is a composition of functions. Its the outer function is e to some power, and the inner function is natural log of x. And since the outer function is e raised to some power, the derivative of that is just e raised to that same power, which is e to the natural log of x. Then the derivative of the inner function would be the derivative of natural log of x, but we don't know what that is, and so we're just going to leave that as is for now. And on the right-hand side, the derivative of x is equal to 1. And now going back to the left-hand side, we can simplify e to the natural log of x as x. And if we then divide both sides of this equation by x, we'll get that the derivative of natural log of x is equal to 1 over x. And so if you see natural log of x on its own and you're asked to take the derivative, you can just know that the derivative of natural log of x is equal to 1 over x. Now that we've gone through this process, you don't need to do it again. You can just know the rule of what the derivative of this is. Now as things tend to go, you might not always have just the natural log of x on its own. It might be a function that involves natural log of x, but to actually take the derivative will require some other rules as well. And as an example, let's find the derivative of natural log of x squared plus 1. And this is a composition of functions, with the outer function being natural log and the inner function being x squared plus 1. And so we do have to use the chain rule to find the derivative of this. The answer is not simply 1 over x squared plus 1. And using the chain rule, we're going to start with the derivative of the outer function. And the outer function is natural log. And if it was the natural log of x, we know its derivative would be 1 over x. And so the derivative of this outer function would be 1 over the stuff on the inside. And so this is 1 over x squared plus 1. That's the derivative of the outer function using the chain rule. And then we need to multiply by the derivative of the inside, which is the derivative of x squared plus 1. And using the power rule and the constant rule, the derivative of that is 2x plus 0, or just 2x. Next, we're going to talk about exponential functions. And we already know that the derivative of e to the x is e to the x, but what's the derivative of a to the x, where a is some arbitrary positive constant? So maybe this is the derivative of 2 to the x. What would that derivative be? And the way that we're going to find this is basically the same as how we found the derivative of natural log of x. That being, we're going to start with an identity that we know to be true, take the derivative of both sides, and then do some clever manipulation to get the answer. And so let's start with the natural log of a to the x, and that's equal to x natural log of a. And that's just one of the logarithm rules from earlier in the video. And now let's take the derivative of both sides, and to take the derivative of the left-hand side, I need to use the chain rule, with my outer function being natural log, and my inner function being a to the x. And with the outer function being natural log, the derivative of that is 1 over whatever on the inside, and that's 1 over a to the x, just like in the last example. And now with the chain rule, I need to multiply by the derivative of the inside, and that's the derivative of a to the x. Now I don't know what that is, that's what we're looking for, so let's just leave that as it is for now. And on the right-hand side, we're taking the derivative of x times natural log of a. And you could do this with the product rule, but it's actually easier than that, because this is a function, that being x, multiplied by a constant, that being natural log of a. And even though I don't know what natural log of a is, since a is a constant, natural log of a is also a constant. So this is a constant multiplied by a function, so I can actually use the constant multiple rule, where I ignore the constant and I take the derivative of the function, and the derivative of x is 1, and the constant comes along for the ride, so the derivative of x times natural log of a is just natural log of a. And now that we've taken the derivative of both sides, let's multiply both sides of this equation by a to the x, and what I'll get left with is that the derivative of a to the x is a to the x times natural log of a. And so the derivative of any exponential is not quite itself, but it's itself times some constant, and that constant is natural log of a. Now let's use this rule in a few different examples. The first example is the derivative of 10 to the x. And this is a very direct application of that rule, and the derivative of 10 to the x is 10 to the x times natural log of 10. It's just exactly what was on the previous slide, but instead of a, it's 10. Next, let's look at the derivative of e to the x. And we already know what the answer should be, but I want to check to make sure that our new rule lines up with our old rule. And the derivative of e to the x is going to be e to the x times natural log of e. And since natural log of e is 1, that leaves us with e to the x, which is a good thing because we already knew that the derivative of e to the x is e to the x, and this just confirms that. And finally, let's compute the derivative of 5 to the power of x squared minus 1. And this is a chain rule problem because my outer function is 5 raised to some power, and the inner function is x squared minus 1. And so we are going to be using the chain rule. And the derivative of 5 raised to some power is 5 raised to that power times natural log of 5, just like we saw above. But now using the chain rule, we have to multiply by the derivative of the inside, which is the derivative of x squared minus 1. And then, of course, the derivative of x squared minus 1 is 2x minus 0. So while you're doing these problems, keep in mind that you might have to use more than one rule, maybe the chain rule or the product rule, just depends on the situation, and every problem is a little bit different.